One of the most important, interesting phenomena associated with acoustics is the so-called Doppler effect. What is the Doppler effect? Suppose a source emits a certain frequency of sound. We call it F. And then there's an observer that receives that frequency, receives that signal. Sometimes the frequency as heard by the observer is not the same as the frequency as emitted by the source. So F can become F prime as heard by the observer. And the reason why this happens is due to the motion of either the source or the observer. So there's a frequency shift from F to F prime, and that phenomena is called the Doppler effect, or sometimes called Doppler shift. It does not only apply to sound, can also apply to light and even the water wave on the surface of the water and so on. So let's look at the mechanism behind the Doppler effect. Again, there are two ways to make that happen. Either the source moves or the observer moves. All right, so let's look at these two cases separately. Let's say we have a moving observer. So look at this diagram here. I have a source emitting a certain frequency with a certain wavelength, and the source does not move. And when I say it doesn't move, it means it doesn't move relative to the medium, which in this case is the air. Okay, and then we have this observer who is approaching the source with a speed VO. Now, suppose he doesn't move towards the source at all. He just sits there and stands there. Then what kind of frequency is he going to get? It's just going to be lambda over V, right? V is the speed of sound, right? And then, this is, if I were to draw his ear right here, this is the ear right here, and then you can observe, those waves passing by his ear, right? And the frequency of that is F, which is V over lambda. That's if it doesn't do anything. That's equal to F. Okay, so and then I have the original frequency, which is V over F. Okay, so F. Original frequency is V over lambda, that is. So what happens when he moves towards the source? Well, frequency is the number of wavelengths that you hear per second by definition, right? So the number of wavelengths that passes by his ear is V over lambda if he simply stands there without any motion. But by moving towards the source, his ear can intercept an additional number of wavelengths, don't you think? Right? Let's say he was originally here, the initial position of the observer, right here. Okay, and then a little bit later, he reaches there. Let's say the time it takes to go from the initial to final position for the observer is 1 unit, say 1 second, for example. During that unit time, how far did he move towards the source? Well, that's equal to his speed VO times the time, which is 1 unit, right? So this distance, let me label that. This distance between his initial and final position is simply V observer times 1 unit, okay? Times 1 unit of time, right? And as he moves from initial to final position, his ears will intercept additional number of wavelengths. How many would he intercept? Well, it depends on how long that distance is. If that distance is 10 times the wavelengths, then he can receive 10 more, wiggles or 10 more counts towards his frequency count. Okay, so the additional number of wavelengths that he can capture by moving towards a source would be equal to the length that he moves towards the source, which is VO, divided by the wavelengths, right? And that is the additional number delta n. Additional number of wavelengths that his ears would intercept per unit time. On top of that, he already receives an original number of oscillations per second, and that is V over lambda, that's F. So what is the total? What is the total number of wavelengths that his ears can intercept during that unit time? That would be n equals to the original number, which is V over lambda, plus the new number delta n. Okay, and that is v over lambda plus v observer over lambda. Here v is the speed of sound. Again, what is n? N is the number of wavelengths his ears intercept per unit time. And by definition, isn't this the frequency? That's just the frequency. Okay, the number of wavelengths his ears register per second as he moves towards the source. And therefore, you're going to get a frequency f prime that is higher than f because the first term on the right-hand side is f. Okay, let me clean this up a little bit. This is v over v plus v observer over lambda, which I can also write as, if I take the v over lambda out, I get 1 plus v observer over v. Okay, so you get this additional factor here, this additional factor, which is greater than 1 in this case, multiplied by the original frequency f, which is v over lambda. So I have f prime equals f times this factor of 1 plus v observer over v. Okay, this is the new frequency heard by the observer as he approaches the source with the speed VO. Along the direction, along the line connecting the source and the observer, he has to move directly towards the source, otherwise he's not cutting into extra wavelengths. Okay, so the directional motion of VO here is from the observer towards the source. Okay, that's implied. Now, if he moves, say, if he doesn't, let's say he doesn't move this way, which is going to increase frequency that he hears. If he moves that way, does that do any job? Does that increase or decrease any frequency? No, because he is not cutting into extra wavelengths, right? Therefore, moving perpendicularly to the line connecting an observer and source is useless as far as acoustics is concerned. Okay, you have to move along the line connecting the source and the observer, and that is the speed that will change the frequency heard. So in our case, he is approaching the source, so you hear a higher frequency. What if he moves away from the source? Then he's going to hear lower frequency because he is not intercepting as many numbers as he tries to escape from the source. He will escape a certain number of wavelengths that he would otherwise intercept if he were just simply to stand there. Okay, and that is when you acquire negative sign in front of the observer. So I can put a positive and negative sign to include both cases. Negative sign applies when VO is away from the source. So you're moving away from the source, you should use a negative sign because f prime is going to be less than f. Okay, so this is the first case of the Doppler effect due to the motion of the observer and the physics here. The basic idea is that by moving towards the source, the observer is cutting into extra number of wavelengths, therefore increasing the total number of wavelengths his ears can intercept per second, and that is to increase the frequency. Okay, so the wavelength doesn't change, but you're simply intercepting more wavelengths per second. That's how you increase the frequency by moving towards the source. Now, the second case is moving, when the source is moving. It turns out you still get a Doppler effect, but the mechanism is different. The formula is also different. So here we consider a case where a source starts from point 0, okay, which is this red dot here in the middle. This red dot here in the middle. And then that source is not stationary. It moves towards the observer Nancy, okay? Moves towards the observer Nancy. So it moves along the line connecting the source and observer again. And a little time t later, the source reaches point 1, which is centered, which is at this green dot. And the time it takes to go from point 0 to point 1 happens to be the time it takes for one period of the wave, which means by the time you first emit a wave at point 0, and that wave starts to propagate, and then by the time you reach point 1, you emit your second wave. Okay, so the time interval between 0 and 1 happens to be one period, just to make things simpler. Okay, and then once you start to emit that wave, which is centered at point 1, the green dot, that wave starts to propagate as well. So you see this red circle centered at the red dot here. That was the the first wave emitted by the source. And then you see this green circle centered at the green dot at point 1, that is emitted a time t later. T is the period of the wave. Okay, and then the source keeps on moving and then it reaches point 2, again a time t later. So that's when it starts to emit the third wave, which starts to propagate. And then that's when you see this blue dot at point number 2, and it starts to propagate. So this wave will make a smaller circle, smaller blue circle. Again, the circle is smaller than the first two because there's less time for it to propagate. Okay, and then finally, that source reaches point 3, the orange dot. That is when it is barely starting to emit a wave. Okay, the circle created is 0 in radius, so we didn't even draw it. Okay, so again, the source went from point 0 to point 1 to point 2 to point 3. Every time it reaches a new point, it emits a new wave. Okay, so how many wiggles, how many wavelengths did it emit? It's going to be the first one, which is orange, the second one, which is green, the third, which is blue, and then the fourth one, which barely started. Okay, now, so if the source did not move at all, right? If it didn't move at all, then no matter which wave it emitted, first one, second one, third one, and fourth one, the center is also always going to be at the red dot, right? Because the source didn't move at all. And therefore, as the first wave reaches Nancy, which is the orange, which is this red one, right? As the first wave reaches Nancy, the last wave is just barely being emitted at point O. Okay, so you see, between the first and last one, you have 4 wavelengths. Okay, but these 4 wavelengths actually, first one, second, third one, and fourth one. In fact, the last one is barely emitted. So you have actually 3 wavelengths. Okay, these 3 wavelengths will stretch all the way from point O here to where Nancy is. Okay, so the wavelengths, you got 3 wavelengths spread out between point O and where Nancy is. So the wavelengths are pretty long. Okay, you just take the largest radius, which is radius of the red circle, divided by 4. That's the wavelengths. But the situation is different now that the observer is actually, the source is actually moving, because the last wave was emitted at the location of point 3. It's just getting emitted, while the first wave still has just reached Nancy. So now all these 3 wavelengths are squeezed between point 3 and where Nancy is. We're looking at a much shorter distance, which is this much. See, which is only this much, instead of the entire radius of the red circle. So you have squeezed these wavelengths into a shorter distance. That amounts to what? A shorter wavelength. Okay, so you squeeze the wavelength. Now remember, the frequency is wavelengths divided by the speed of sound. The speed of sound doesn't change, but the wavelengths did. It became shorter. Okay, the speed of sound, I'm sorry, it should be, the frequency is actually equal to the speed of the wave divided by the wavelengths. The speed of sound does not change if the wavelengths get shorter, and therefore, what happens to the frequency? It will increase, right? So because I have, let me write that down. F equals to V over lambda. Okay, but that's the frequency of the original, emitted by the source. The frequency heard by Nancy depends on the wavelengths of the wave that reaches her ear. That's lambda prime. As we saw, lambda prime is shorter than lambda because the waves get squeezed as the observer, as the source moves towards her. Okay, so since lambda prime is shorter than the original lambda, F prime is going to be higher than F. F equals to V over lambda. That's the frequency emitted, and F prime is the frequency registered by Nancy's ears. Is going to be higher than F because, again, lambda prime is shorter than lambda. So basically, the mechanism of how a moving source can change the frequency heard by the observer is because by moving towards the observer, you are squeezing the wavelengths to make it shorter. So here it's not because motion of the observer, it's because motion of the source, which changes the wavelengths. Okay, so that's a different mechanism. Now, exactly what is F prime equal to? Well, we can look at this diagram below, and we can see here. Initially, the source is at point A, okay? And the observer is at point B. let's say the source emits a whole bunch of waves, and a time t later, the source, the first wave emitted by the source will reach from A to B, and then how long is that time? Well, that depends on how fast the wave propagates. That speed v, that's the speed of sound. Okay, so the length AB would be equal to the speed of the sound times the time it takes to go from A to B. Okay, for the source to go from for the sound to travel from A to B. Okay, that's A and B. Now, in reality, the source actually moves. So by the time the last wave is emitted, the source has reached point C. Okay, so what is AC equal to? AC equals to V source times T, right? So therefore, the original number of wavelengths would stretch between A and B. Now it's squeezed between C and B. Okay, so original wave, the number of wavelengths is the same emitted by the source as it moved from A to C, or whether it doesn't move at all, because it's got a given frequency, it has to emit a certain number of wavelengths during a certain amount of time t. So that's the same whether he moves or not. But by moving from A to C, all these wavelengths, same number of wavelengths, is now squeezed in a tighter space between C and B instead of between A and B. So therefore, you're looking at a compressed wavelength. Lambda prime is going to be shorter than lambda. How much shorter? What's the ratio here? The ratio equals to what? The total amount of lengths occupied by these wavelengths. Okay, lambda prime is proportional to the distance between C and B, because all these wavelengths is squeezed between C and B. Okay, this length. I can actually take C and B divided by N. N is the number of wavelengths emitted during the time t. Okay, but lambda would be stretched between A and B. That's when the source is not moving at all. Okay, so you take the total lengths A and B, then you divide it by the total number of wavelengths. That will get you the original wavelengths. Okay, I don't care what N is, it cancels out. I don't care what T is, it all cancels out. Okay, but what's important is the ratio of CB over AB, and CB, as you know, is AB minus AC. Okay, so AB minus AC, so we have VT minus V source T. And we divide by AB, which is VT. Okay, you can see T cancels, so you're left with what? 1 minus V source over V. Okay, so lambda prime indeed is shorter than lambda because the right-hand side is less than 1. Okay, but the frequency is inversely proportional to the wavelengths, isn't it? Right, inverse proportional. So therefore, I have F prime over F is equal to lambda over lambda prime, so inverse proportional to. Okay, so but what is lambda over lambda prime? It's the inverse of this quantity, which is lambda prime over lambda, right? So I can now write it as what? 1 over 1 minus V source over V. Okay, so now I'm able to find the expression F prime now. F prime equals F times this factor here, 1 minus V source over V. Okay, you notice this formula is different from the one that we found earlier for the motion of the source of the observer, because the mechanism is different. Okay, here you have the motion of the source squeezing the wavelengths. In the first case, you have motion observer picking up extra number of wiggles. It's different. This one, as you can see, is in the numerator. The correction is in the numerator, whereas in the first case, the correction is in the denominator. So it's different. You can see in the first case here, the correction, okay, is, you don't have everything in the denominator. Here you have 1 plus something. Okay, so the answer is different. You have this extra factor here, which is this. It's all in the denominator. Okay, so again, you have to understand the physical mechanisms for both the source moving and the observer moving. They're different. One more time, the source, when the observer moves towards the source, the observer picks up additional number of wiggles. additional number of wavelengths, therefore increasing the frequency, which is defined as a number of wiggles captured per second. And when the observer moves towards the source, the observer is squeezing the number of wavelengths captured during the same amount of time, because the total length between the first wave and the last wave is now shorter. Okay, for shorter wavelengths, you're going to get higher frequency. Of course, when the observer moves away from the source, that you're going to stretch the wavelength. So Pablo, in this diagram, Pablo is going to detect a lower frequency than expected, because this time you got the wavelengths getting longer, because the first wave he receives is here, but the last wave he receives is not at 0.0 anymore. Rather, it's at 0.3. So the distance between him and the 0.3 is of course longer than the radius of the red circle. Therefore, the wavelengths that he receives get stretched. A longer wavelength translates to a lower frequency. Okay, and all you have to do really, as far as math is concerned, is just to change the sign here, this negative sign, to a positive sign. So you have a bigger denominator, then expect therefore a shorter, therefore a lower frequency. Okay, so those are the two mechanisms. Now, what happens if you combine? What happens if you have both? By the way, you have another visual illustration of the Doppler effect with both mechanisms. Here, the first diagram is when the source and observer neither is moving. Of course, you don't have any Doppler shift. The second case, when the source moves towards the observer Y, and the third case is when the source is not moving, but the observer is moving either away or towards the source. Okay, so what if both are moving? Well, we're going to have to combine the effect. Okay, so both sources are moving. F prime has to be equal to F times what? Well, when the source is moving, when the observer is not, then you have this factor here, 1 minus V source over the speed of sound, right? And when the observer is moving, the source is not, you have this extra factor of 1 plus V observer over V, right? And you have to multiply by both factors if both the source and observer are moving, okay? And then we can clean things up a little bit, and then we get F times what? We multiply both the numerator and denominator by the speed of sound V, then I get this. I get V plus V observer, and then V minus V source. Okay, assuming that the observer is moving towards the source, and the source is also moving towards the observer. So you have the plus sign in the numerator and negative sign in the denominator. This is when you combine them. Now, what happens if the observer moves away from the source? Then of course you have to use a negative sign here, right? A negative sign here. And when the source is moving away from the observer, you have to use a plus sign here, right? The sign has to be reversed. A lot of people seem to have some trouble choosing the correct sign when it comes to solving a natural problem when the source and observer both move. So here's a little trick how you can keep the correct signs. When both the observer and the source are moving, in order to determine the signs in the numerator and denominator, please do that one at a time. Okay, when you want to determine whether the numerator, the sign in front of V observer, is that plus or minus? That is due to the motion of the observer, right? When you pick that sign, please ignore the motion of the source. Okay, that is, you treat the source as stationary. Okay, let's look at an example. Suppose I have a case where the source is moving this way, that's V source, and the observer is moving that way, also in the same direction, V observer. Okay, on the line, both in the line connecting the source and observer, so they should both count. When you determine the sign for the numerator, do you use a plus or minus sign? Well, to make that decision, ignore the motion of the source for now. Okay, so you stop this guy from moving. It doesn't move at all. now you see the observer is moving away from the source. That clearly will decrease the frequency, right? So how do you decrease the frequency? You make the numerator smaller. Okay, so you choose a negative sign, right? So you choose, f prime would be equal to f times what? V minus V observer. Okay, V minus V observer in this case. Now we can pick up the sign for the denominator. For the denominator, it's the observer that's stationary and the source that's moving, if you want to determine the sign. So we ignore the motion of the observer now. You only see the source. This time the source, you can see it's approaching the observer, and that tends to what? To increase the frequency. So f prime, how do you make f prime greater than f? By doing something to the numerator, you choose a negative sign. That's how you make the denominator smaller and therefore increasing f prime. So you see, you're getting two negative signs in this case. Okay, so that's how you choose the signs. Do that one at a time, stop the other one, and look at what happens. Does it increase or decrease the frequency? And you choose the signs accordingly. Okay, now an interesting special case based on what we just found, this formula here. This formula here is what if Vs equals VO. Both the source and observer are moving at the same in the same line connecting them, and they're moving at exactly the same speed. Okay, exactly the same speed. So you have V minus VO divided by V minus Vs, but Vs and VO are equal to each other. Then you have what? F equals F prime. Okay, that's a special case. So suppose I'm driving a car, and the car behind me honks at a certain frequency. Now, if I drive slower than that guy, so the guy is approaching me, okay, then I'm going to hear a higher frequency than the actual frequency of the horn. On the other hand, if I drive away from the car behind me, we're both driving in the same direction with exactly the same speed, I'm going to hear the exact same frequency as the original horn, because the two effects just cancel out, as you can see. Okay, so you're going to have a difference in either the direction of motion or the magnitude to observe an actual Doppler effect. All right, we're going to look at some more numerical examples on how Doppler effect works. But before that, we can look at some qualitative applications, some examples of qualitative application of Doppler effect. This is an illustration of the so-called Doppler ultrasound. You know what an ultrasound is, right? It's a medical term, and basically, an ultrasound, in an ultrasound situation, you have a device which emits a beam of ultrasound, which is a beam of sound with a frequency higher than we can hear, higher than 20,000 hertz. Okay, it can penetrate through our skin, and it can reflect off of organs such as the liver, and that gets reflected, gets picked up by a device, and then will be translated into a visual signal on screen, so we can get a picture of what's inside our body, such as our liver. Okay, so it's a medical application, but a normal ultrasound can only give you a stationary picture of your internal organs. What it doesn't do is it doesn't detect any motion. Okay, it's like taking a snapshot. It doesn't detect any motion. Sometimes though, we need to know how fast the blood flows through an artery. How do you detect motion? How do you find the speed of the blood flowing through an artery? This is when a Doppler ultrasound comes in. So the Doppler ultrasound not only detects the signal, which is reflected ultrasound off of your body, it also detects any frequency shift. Okay, any frequency shift. So it emits a sound, right? Emits an ultrasound this way, and gets reflected. The sound gets reflected. If the reflected signal has the exact same frequency as the emitted signal, then guess what? Whatever target that it reflects off, this is the target, is not moving relative to the source, which is the ultrasound device. Okay, but if the reflect frequency f prime is higher than the original frequency f, what did that tell you? It means the reflector is moving towards the ultrasound device. Okay, this reflector could be the blood flowing in the artery, and if it flows faster towards the observer, then F prime is going to be higher than expected. So when you detect the frequency shift between F and F prime, you can find not only a stationary picture, but in addition to that, you can find the speed of the blood flow. Isn't that cool? Right? That's called Doppler ultrasound. So it's in addition to the regular ultrasound, it detects the speed of the blood flow. Now, another useful application is actually beyond acoustics. It's Doppler effect applied for radar. We're not going to talk about too much details how radar works. It's not sound wave. It's actually electromagnetic wave. But electromagnetic waves, just like sound waves, have Doppler effect as well. Okay, so it's basically, this is the picture of a large-scale Doppler radar for weather detection. So it emits a radar signal, okay, which is an electromagnetic wave. It gets reflected, gets bounced off a piece of cloud. Okay, so you have a piece of cloud. Okay, it gets bounced off. If that piece of cloud is moving towards the radar station at the time, okay, moving towards us, then the reflected signal is going to have a higher frequency, don't you think? Okay, reflect frequency is going to be higher due to the motion of the observer. Actually, due to the motion of the source, the observer, the radar station is not moving. Okay, so F prime is going to be higher than F due to the motion of the source, which is the source. Because the reason why I call it source is because this is the source of that reflected signal. Okay, the original source, of course, is from the radar, but when the radar receives the signal, the radar becomes an observer, and the source is the cloud that bounces the radar signal off. So F prime is now greater than F. Okay, and by detecting the difference between F prime and F, you can figure out how fast that piece of cloud is moving towards us. So that's why you can predict. You can make predictions. Oh, it's going to reach us in half a day or whatever, because you know the speed, which is how fast this piece of cloud is moving. So that is quite useful in weather forecasting, as you can see here. Doppler radar live stream. It measures the speed of the cloud in real time. Okay, there are many other applications of Doppler effect, including in astronomy, the so-called Doppler, gravitational redshift or blue shift. These things, we're going to see more of that when we study more examples of Doppler effect beyond acoustics. So in the next lecture, we're going to look at some couple of examples of how Doppler shift works in acoustics. All right, so that's until the next lecture.